Hiya.
Hi, Raj.
Hi, Tommy.
Are they on yet?
No, they're not.
I wonder, could you just send her the thing again?
I just did. I just did now. I know it was a bit confusing that I sent a link for the first half and the second half, but I did. So I've just sent the link for this session just
You
now.
have said you've just sent it to Edosa, have you?
Yeah, that's right.
Oh, that's great. Because I think I may have sent her the wrong link because we had something, for Monday's Bedford session, and um, that was last week, and that was for 4:30. And
Um,
I just hope that they've got the link on now.
no, no problem. Well, I've just sent her the email. So
You
we'll
have.
see what she says.
Yeah, great. Thanks so much. God, I had a slight moment of panic there.
No point. No problem. Me too. I was thinking,
Yeah.
I got the right day, isn't it? But yes, we're both here, so it must be in the right place.
Okay. Um, I, yeah. Anyway, if you've just sent it, that's fine.
No problem. Yeah,
Yeah.
we'll see.
Yeah.
I'll just watch my emails in case she emails back.
Yeah. Because I sent it this morning and I have a feeling I may have, there were two Monday sessions and
Mm.
I have a feeling I may have sent her the wrong one.
All right. Okay.
But anyway, if you just sent her another one, that's fine.
No problem.
Yeah. I've just been trying to teach myself electricity. And,
Oh wow.
the more I go into it, the harder it seems.
It's because you can't. It's the same with magnetic fields. You can't see it. You can't.
What?
If you look at a wire and you
No,
say, "Is there electricity flowing through the wire?" Nobody can tell you.
no.
Um, yeah, until you connect something to it. So it's quite odd
Yeah.
in that way. With its forces and you've got gears and levers and things like that, you can see the thing moving around.
Yes.
But electricity, you can't see it until you start.
You've just got to imagine it all the time. And I always get involved. I always get confused between voltage and charge.
Mm. Yeah, well, I've got a very nice picture where it's got the charge is the thing that's going through. It's got like a little chap, and he's getting pushed through the pipe by the voltage. So the voltage is the push.
The voltage is the push, and the charge is the result. Is it?
The thing that goes through is the thing that.
Yeah. Okay. Yeah. Okay. Thanks.
Um,
I mean, I think that um, um, you can always do a hell of a lot worse than ask them just to define a few simple things at the beginning so you can see how they are.
yeah, yeah. Well, that's my plan. Is I'm going to do some diagnostic questions, um, and then see where they're at and how confident they are as well. So not just them, but their students.
Yes.
Although, sure where they are. Let's see if they've emailed back.
Um,
No.
her email is quite difficult because her last name is it's Egg Harevba.
Yeah. Yeah, I just copied it from the previous one at
Yeah.
harrietjarrett.org.uk.
What?
Yeah, I've got it here. So e.eggcarver at
Egg Harevba. Yeah.
harrietjarrett.org.uk. Hmm. And I did my first Planet Possibility session the other day.
Did you? How many people did you get?
I think it was about 8 or 9.
Oh, that was not too bad because the numbers haven't been staggering.
It's a tricky time of year.
Yeah, really it is. Uh,
My partner works for an educational kind of, she does CPD and things like that in the education sector as well. And she said the head teacher she's working with, she feels more like that she should kind of do some kind of taking care of the mental health and all that kind of stuff rather than actually doing CPD. I think people are at a bursting point in a lot of schools at the moment.
yeah,
So it's quite good that some people are still managed to find the time in their busy days to engage with CPD.
yeah. Now, where are they?
Hmm.
I hope they haven't. I hope they haven't got mine.
No,
Yeah,
but then they would have kind of cottoned on.
I passed on, but I may by mistake have passed on last week's, which starts at 4:30.
Okay.
But you've just sent them the one for today, haven't you?
Yeah, yeah, but if it's at 4:30,
Well, it should start at 4:10.
hmm, okay. Oh, were they scheduled for 4:10? In that case, it's only three
Yeah,
minutes.
4:10. Yeah,
Yeah. If they're scheduled, yes, in that case, yes, it's only 3 minutes gone. They're probably just getting settled. We'll be on. We can wait a little bit longer.
Raj, you just might find it good idea to send it again.
Will do.
Does
Uh,
it does say E.Egharevba.
hmm.
Is that right?
Yeah, that's right.
E.Egharevba at at harrisgarrard.org.uk.
Yeah. Okay, sent that link through again.
Yeah.
And I've CC'd you in as well.
I might just go and go out and send her an email saying, that the link is also in your email.
No problem. Yeah.
Yeah,
Uh,
I'll come back again.
just in case I'm going to her junk or something like that because I've never
Yeah.
sent her an email directly before.
Okay.
Hello, I'm so sorry. I had another meeting. I'm really sorry, Raj.
That's all right, no problem. Fantastic. It's good to see you now. Are you there with your department?
Yes, yes.
Fantastic.
Hi, Adosa.
Hello.
Hello. Did I send you the wrong link?
No, it was me. I had another meeting, and if I'd realised, I would have
Oh,
forwarded.
that's all right. No, just we thought something had gone wrong our end.
No, no, it wasn't you. Sorry, it was me.
Ah,
Sorry,
sigh of relief.
Fantastic. Who's in the room with you?
So we've got 4 other members of staff here with us. So we've got Majid, he's a trainee teacher. We've got another member of staff, Kim. She's an established teacher with us. We've got Aidan, another trainee teacher, and Vasilina, and I think she's done some of this with you already. In Bromley.
Oh yeah, brilliant, fantastic. Guys, this is a session just for you as well. So I don't know, can we get your camera on? So and then just wave at me, shout at me if there's something that doesn't make sense, or you've got a question that comes to you. You know, you're the participants who are here.
Yeah.
So yeah, just give us a shout and we'll go at kind of your pace while we go through. So I've got some kind of questions there just to start us off with. But what kind of timings were you hoping for then? When were you hoping to end? Because I want to obviously I don't want to keep you.
Yeah, so it was supposed to be an hour, but obviously we'd have to be sorry to say we have to cut it short a little bit. So till 5 to 5:10, that's all right.
Oh, okay, fantastic. Yeah, that works great for me. So what I'll do is if I try and finish at 5, and then we've got about 10 minutes to fill in the evaluation form, and then any questions or anything else that you comes up as well, we can give you a good chunk of time for that. But as I say, interrupt me. You know, this is the session for you. So yeah. Give us a shout if we go through anything that doesn't make sense or anything you want to do in further detail and so on and so forth. Is that cool?
Yeah.
Fantastic. Okay, let's get going. So my name is Raj Joshi. I'm a physics teacher at Dulwich College, and I'm also chair of the London region of the Association of Science Education. I do a little bit of some bits and pieces with Physics Partners, some bits and pieces with STEM Learning as well. I'm ex-Harris, so I've hopefully kind of sat where you've sat in terms of dealing with the kind of challenges that you have and the kind of catchment that you guys have as well. I was based at Harris Crystal Palace when I started my career and was physics ESS for the Federation. I then moved to the Science Museum group for a bit. Then I was a head of physics in East London, in Ilford. Worked for the Institute of Physics as a trainer. Then I worked down in Stockwell for a bit at an inner city school there. And then before I went to Dulwich, I was school improvement director for a multi-academy trust based around Bromley. So today we're going to have a chat about electricity, and I'm going to kind of delve into some of the misconceptions and things like that the research suggests your students will have in their head coming from trying to understand electrical circuits and what we can do about those, and also kind of thinking about how we think about electrical circuits, because Tommy and I were discussing earlier that it's quite tricky to understand electrical circuits because you can't see what's going on in the wire. If I held up a wire and waved it at you and said, is there electricity flowing in this wire or not? We can't see it in the same way that we can see a force making something move or a lever or something like that. So it's quite tricky to get our head around it. And one of the ways that we can start our students off is by asking a question like this. So which of these do you think our student would agree with, our students in our class?
It says the electric current is in this is the same in both wires. I think there is more electric current in the wire coming from the lamp, and there is more electric current in the wire going to the lamp. Maybe you need to come nearer because I think we're going to be looking at quite a few of these.
Yeah, we are.
Hello, I'm really sorry. I'm just going to say I can't get the camera on, so sorry about that.
Oh, that's all right. No
I
problem.
can remember staff try and help me as well. I don't know why it's not coming on. So sorry.
The other thing I'll say from a practicality point of view is if we cut out, I think I'll send you a link to a second Zoom call. So if this one times out,
Yeah.
send that to you. Okay. I'm going to park this and I'm going to show you another one, and then we're going to come back to it in a little bit after we've covered some bits and pieces. So I'm going to leave you in the lurch a bit and give you another one. And this is an interesting one to show the students. What do we think our students would say?
Yeah, third or wow, or the second.
Okay, let's have a look at a few kind of ideas and bits and pieces, and then we're going to come back to both this one and the previous one as well, and try and work out what the right answer is and how would we teach our students if they were saying an answer that we wanted them to say a different answer. So this is another way that we can ask our students what was going on. So we've got an electrical, you've got a battery with 0.6 amps a current coming out, you've got a resistor, and then you've got a different component there, a bulb. And so we can ask our students, okay, you've got a resistance coming up there. And we can say, what's the current through the resistor? What's the current through the bulb? And often the choice that a lot of students will make will be C. That will be a really common incorrect answer. And the reason for that is that students feel that our current will split evenly between the two legs. Okay. So instead, what we're expecting is we're expecting our answer being D. We're actually got less current going through our top one than our bottom one. Is that something you've seen before? Is that something that you think students would be saying for you guys, or?
Yeah.
Yeah, and we can have a bit of a delve in and kind of have a look at that. What's really nice to ask them about with this is saying, what would you say is the best reason for this? And again, a really common answer that students will take will be A, which really tends to point to the idea that students will feel that the current is used up rather than this continuous amount. So our kind of best value that we want to say is that the current through each branch adds up to the current through the battery. So we've got 0.6 coming out here. We've got a certain amount coming out here. It's conserved coming out. And then we've got the certain amount back. Okay. So this is the kind of outcome we want to get our students to do. I've put into these slides some kind of explanations and what the research says about this as well. I think I'm going to move on for this, but the other thing that you can do when you do these diagnostic questions at the start of the course and working out what students think at the moment is you can ask them to kind of bet and make value judgments. So say that you've got 10 counters on here, and you might say that I'm pretty sure, so I'm going to bet 5 of my counters being on it true. B, I'm not too sure. I'm only going to bet 2 of my counters, and then C, I'll bet the last 3 on there because I'm much more sure about A than I am about B and C. So with this one here, A is going to be correct, B is going to be correct, and C is going to be incorrect. So we can try these kind of diagnostic questions, start our students off with questions like these, or even concept cartoons like these. Try and have a look, see what we understand, and highlight any misconceptions, see where we're at, how much do they know. And once we've got a good idea about how much they know, we can start to deliver our electricity schema work and have a look at what they know already and try and build on that and try and get them on the right paths. So what I would suggest is thinking way back to Key Stage 2. And what students will have typically done in primary school is they will have classified things from as conductors and insulators. So they will have put these things in electrical circuits and seen usually if the bulb lights up. And then what you can do is you can start to link this to an understanding of charge. So you might show them 2 charged balloons. Say this one is negatively charged, this one is positively charged. What happens? In this case, they move together. Then you could start to ask them to explain why does this happen? So you've got opposite charges, they pull together. You could then start to direct these into more formal terminology. Rather than saying they pull together or things like that, we can start to use words like attract or repel. So we're just initially at the start of our electricity topic talking about charges. We know that some things are conductors, some things are insulators, and we can start to talk about what do we know already about charges. Using our correct terminology. Okay. Then looking at unlike charges, again with our correct terminology, talking about them repelling each other. And explaining why. Making sure that we don't fall into our kind of traps of saying, okay, there's one rule for positive and one rule for negative, but actually we're talking about like or unlike charges. And then doing the same for 2 negative charges as well. Okay. And then you might want to introduce the idea of how these things feel a force and a distance as well. So we have these 2 balloons that are quite close to each other, and the same balloons move further apart, and saying what happens with them. So they're repelling each other with less force as we go through. And starting to talk about, okay, right, there'll be forces on charged particles, and the force between them will depend on the distance between them as well. So the electrostatic force will get smaller further when the charges are further away. We can then start to link our physics knowledge with successes that they would have had in chemistry. So we've been talking about charges. We can talk about what we know from Key Stage 2 in terms of conductors and insulators. But we can also link that to chemistry and link that to what we understand about metallic bonding, how those free electrons can move. At the moment in chemistry, we tend to just say they can move. But our understanding of that was those electrostatic forces can say, okay, there's a certain direction that they'll move. And if they bunch up together, they'll try and spread out a bit more. Those are free electrons, and they'll move around there. Then I think even though you're aiming to teach about current electricity, it's really good to get that Van de Graaff generator out. If you're feeling a little bit not too confident using it. The CLEAPS resources are absolutely fantastic in terms of really taking you through step by step how to use them, what's safe, what's not safe, and how to use those Van de Graaff generators in a certain way. That's Van de Graaff there in the middle. But I would suggest, before we start to talk about anything to do with current electricity, having a go at talking about these charges and get them to feel this build-up of charge within the Van de Graaff. Have you guys got a Van de Graaff? How does it work? Does it work well?
Yeah, it's well, as long as if it's a bit damp, it's not so great, obviously. Yeah, it works.
Yeah, so it's worth getting it out and saying, okay, we've got this build-up of charge. You can feel the kind of tingliness of it, things like that. I used to have my old mortarboard. So if we had students who had very short hair or very curly hair, I used to get them to put my old mortarboard on, and a little tassel thing used to stick up. So if you've got something like that, a hat with a tassel on the top, then that's quite good for that. So once students have this kind of concept of charges, and there are charges within the wires, and they can move about because then we've got metallic bonding, and if there's a buildup of charge, the charges will want to move away. We can start to talk about gaining charges, again using static. I'm going to whiz through these, but I'll give you these slides. And then we can start to use this electrical terminology. There's a lovely video by Ted Ed, which looks at the electric vocabulary and how people like Benjamin Franklin came up with some of the words about charge and discharge and all of those kind of words. But we can start to define our terms with students once they've got an idea of that. We can talk about energy and linking energy to our previous encounters with it within the physics scheme of work. And we can talk about energy being this capacity to do work, energy being measured in energy being measured in joules. We can look at charge, this quantity of charge, which is why we use the letter Q to represent it being measured in coulombs. One of the things that you might want to say how many electrons in 1 coulomb, because it's quite a lot. A coulomb is a big old, I use the term bucket of charge. So I imagine that we've got a big bucket and it's full of loads and loads and loads of electrons. And that's what a coulomb is. And we can talk about time and say time is measured in seconds. And if you want to be incredibly philosophical, maybe you wanted to ask them what the meaning of time is, but maybe that's left to our religious studies teachers or our philosophers rather than us scientists just now. Then we can introduce our kind of 2 key terms that we're going to be talking about all the way through the electricity topic: potential difference or voltage, which is our difference in electrical potential energy per charge. So if we've got each of those little electrons, they're holding a certain amount of energy, and it's the energy per charge. If we want to find out the total amount of energy, we can just add these up together. But actually, the big concept that students really struggle to understand is that we're talking about the energy per charge. And there are a few different little analogies and things like that we can use to understand it that we'll have a look at in a moment. Then we've got current. Current used to be known as electrical intensity. So we have the letter I. That's measured in amps. And that is the amount of charge passing a certain point within a certain amount of time. So I kind of get students to think about, okay, maybe we've got like a speed camera or something like that driving along our road. And this speed camera is going and it's flashing and counting the number of electrons going past. So we can think about current as this kind of flow of charge, maybe with analogies of our kind of flow in a river, but it's the amount of charge per unit time. Once students are happy with those, we can talk about resistance, where resistance measured in ohms is the voltage or the potential difference through a component divided by the current going through it. And we can also talk about power, which is the current times voltage. And you can always make that lovely physics joke that we can make every year and ask our students, what's the unit of power? And they say watt, and then you say, what's the unit of power? And you can see how many times you can go round and round with that before they start groaning. So we can label our different terms. So we're going from this conceptual understanding of charges and what they are, what's inside those wires, how they're moving around, to saying, okay, we've got special words, special electric vocabulary to describe these different things. And this is how they're related to each other. And we can use that. My students always chuckle at this picture, but I show it every year. I always quite enjoy it, and saying, okay, right, we've got our volt. Our volt is there. It's the thing that's pushing it. It's the energy per charge, pushing that current, that amp through, and our resistance thing there at the top. It's restraining that current. It's stopping that current through. So the volt needs to push extra hard if that resistance, that ohm, is pulling it on there. And this idea of saying, okay, we've got pushing, we've got our resistance restricting, resisting it, and our current is flowing. These words, these verbs can be really useful if we emphasize them with our students, for them to really kind of get an idea of the concept and what's going on, but start to build those mental models with the. And so once we've got that, we can maybe use our kind of real context. So we can talk about pylons. Now, living in London, we might not see great big pylons like this. And we can maybe talk about energy being generated somewhere that's kind of windy, like out in Wales, or energy being generated for somewhere that's got great big gorgeous mountains where we can build reservoirs like out in Wales, or areas that have a history of coal mining, and therefore they're a great place to build coal-fired power stations like out in Wales, for example. And you can say, okay, the electricity is being generated there, and we can look at these pylons, this network of pylons and cables, our national grid, and talk about how we're going to be getting our electricity from there all the way to where we are in London. And we can say those wires, they're really, really long. And start to say, okay, right, we've got this same thickness of wire, but they've got different lengths. And we could ask our students, well, do they think these are right or not, and how confident they are. Do you guys want to have a chat? What do you think is correct? What do you think about A, B, and C? And then just shout out and let me know what you think. So we're thinking about charges, we're thinking about things flowing, we're using our knowledge from chemistry and from metallic bonding and things like that. We're talking about the charges on those balloons, how they're going to be moving through it. What do we think?
Everything about A, I don't think it can be right. So A, they can't all be the same. So what would you go for? I am sure this is right now. I'm sure this is wrong. Yeah, thank you, Kim.
Are you going for I'm sure? Not even, I think, a nice confident one there. Fantastic.
The next one, the long wire has the biggest resistance. Yeah. increases. So I think we're sure that's right.
Are you thinking or are you shoring?
We're sure in.
Nice. Okay.
Resistance of the short wires adds up to the resistance of the long wire.
And if you want to go up to the screen and measure them with your
Oh, right.
as of this size.
Oh my life.
If they're supposed to.
If
be,
they're all,
yes.
I've got a little ruler here, not the best.
Guys, we're just about to end this Zoom call. Have you got the link to the second one?
Yeah. We might get a picture this time. All right, sir.
I'll see you on the other side.
All right then. Thanks. Bye.
Tom, is that okay? So just the second link.
Yep. She said yes. Close out this. That's going to.